When people hear quantum computing, they picture a blackboard full of equations. Something very abstract, very theoretical. But in reality, this is mostly engineering.
You're not staring at equations all day. You're building things with your bare hands, and it's way more physical than people expect.
For years, we focused on controlling a single cat qubit, understanding the physics, making sure it behaves exactly the way we want it to. Now, the question has completely changed. It's not does it work anymore. It's how do we build hundreds of them. That's why we built this place. It's one of the largest quantum engineering labs in Europe, and this is where we go from research to product.
It all starts with a chip. A qubit is a tiny superconducting circuit, and we fabricate these in a clean room. You never get the chip right on the first try. That's just how nanofabrication works. You make one, you test it, you learn something, and you make the next one better. We're working at the scale that's smaller than a bacterium. At that level, a tiny defect, something you literally cannot see, can completely change how the qubit behaves.
The space has to be sealed off to prevent contamination, so we don't introduce anything that can interfere with the chips. We built a filtration system that recycles the air 60 times an hour.
The real challenge isn't just making one great chip, it's making them consistently. And if we can make them more reproducible, then we can scale. And that's the whole game.
What's exciting about this new facility is that we will have a state-of-the-art nanofabrication cleanroom dedicated not just to research samples, but to actually produce the next generations of Alice and Bob processors.
Once the chip is fabricated, it has to be operated near absolute zero, the lowest temperature that physically exists. This, right here, is literally one of the coldest places in the whole universe. That's what the physics requires. But when you cool something down to milli-Kelvin temperatures, everything shrinks. Metal contracts, interfaces shift. Something you align perfectly at room temperature is not aligned anymore when it's cold. It's not just about temperature. Magnetic fields are a huge problem inside the cryostat. Even the Earth's magnetic field can interfere. So we shield everything with mu metal, and every component has to be non-magnetic. You can't use a regular screw. You have to think about every bolt, every wire. Working here changes the way you think. You start worrying about things that would never cross a normal engineer's mind.
Even the building has to be engineered for quantum. A truck driving nearby can create enough vibrations to be a problem. So we tested the entire site, vibrations, magnetic fields, everything. We had to make sure that the environment itself wouldn't mess with the physics.
In this lab, we are going to have 20 dilution refrigerators. That's not a research setup anymore. That's really an infrastructure. And what we really need are the people who can operate them. A variety of engineers who understand all the aspects, who can work with these systems day to day.
To control a qubit, you send it a microwave pulse. It's a signal at a very precise frequency. When it hits the right spot on the chip, it resonates. Everything has to be exactly right. The frequency, the timing, the amplitude. If any of those one things is off, even slightly, the operation fails. And when you go from one qubit to dozens to hundreds, all of these interactions multiply. The complexity just explodes. Our signals move on nanosecond timeframes, and at scale, these interactions compound. Each component in the chain shapes and conditions the final signal. Even the cable length becomes part of the timing architecture. It's a bit like tuning an instrument, except the instrument's at millikelvin and precision is everything. This is the connection to the cryostat, is this Fisher connection over here.
We're past the prototype stage now. This isn't one experiment on a bench anymore. We're building actual infrastructure, and that requires a different way of thinking. The electronics inside the racks are extremely sensitive to temperature fluctuations. Even small changes can affect the stability of the electronics. So we built a cooling system for the racks, something you can see in modern data centers. It's extremely precise and efficient.
Soon, we will need dozens of chips working together, communicating with each other in real time. That's why this lab exists, not to explore whether it works. This is about scaling it up.
Everything in this lab was designed from the ground up for exactly the conditions we need. My job isn't to stabilize a chip, it's to stabilize everything around it. Air temperature, humidity, vibrations, cabling, grounding, every single parameter has to be controlled. The performance has to come together at the system level. If the system doesn't work, the physics doesn't work. And this is what makes system engineering so critical. Okay, so I think we're good.
A few years ago, we are still proving that CAD qubits actually work. Now we are building the place where they scale. And it's a pretty exciting moment to be here.
I'm not going to sit here and pretend like we're done. Quantum computing is not finished.
But every iteration, every cooldown, every test, we get closer.
At some point, you look back and realize this is actually becoming real. It's going to be built by engineers, and we are just getting started.